Hello our viewers. On our previous discussion about rotational motion, we have tried to define some of the common terms used under angular motion. We have defined angular displacement. We have tried to see angular velocity, angular acceleration. As well, we have tried to correlate with that of tangential velocity and tangential acceleration. Angular velocity can be given as linear velocity over radius r. Angular acceleration can be given as linear acceleration or tangential acceleration over radius r. It's also possible to have the angular displacement as linear displacement over radius r. We have also tried to see about centripetal acceleration. Acceleration appears due to the change of velocity in direction, as acceleration or centripetal acceleration is equal to r times the angular velocity squared. We have also tried to see about centripetal force, as mass times the centripetal acceleration can be related using mass times radius r times angular velocity squared. And at last we have tried to discuss about the direction of the angular velocity and angular acceleration are always along the axis of rotation. They might have the same axis, the same direction if there is a fast moving object, fast rotating object, but if the rotation is gradually decreasing and decreasing, angular velocity and angular acceleration has opposite direction, but it should be along the axis of rotation. So that was what we have discussed previously. So for today we'll try to see about the different types of motion under kinematics that you have already learned and related with that of the angular motion. In translational or a linear motion, you have learned that depending on acceleration, we can classify motion into three, as uniform motion, uniformly accelerated motion, and accelerating motion. Uniform motion is a motion with zero acceleration, velocity remains constant. But for uniformly accelerated motion, there will be a change of velocity, but that change of velocity is constant. That means the acceleration remains constant. But in the case of accelerating motion, you have learned that the object tends to have a different acceleration, and acceleration might be depends on time or displacement. Here, in angular motion, we are trying to deal about the uniformly accelerated motion. We are assuming that the angular acceleration remains constant. So for a rotating object with a constant angular acceleration, we do have a different axis or a different equations, and we'll try to apply those equations. So when a rigid body is tending to rotate about a fixed point, let's assume that here you have a compact disk. Let's say that here the disk has different points. Here point A, point B, and point C. Different location, we have different points. And let's say that this CD tends to rotate on one direction. Let's say that it's tending to rotate counterclockwise. So on this CD, we have different particles. All of these particles, they do have the same amount of angular velocity. They all have the same angular velocity, and they all have the same angular acceleration. But since they are found at different locations from the axis of rotation, they say that here you do have point A, point B, and point C. Point A is 23 centimeters away from the axis of rotation, and here you do have point B. Let's assume that it is found at 58 millimeters from the axis of rotation. So point A and point B, point C, all of these points have the same angular velocity as it tends to rotate. If the angular velocity is 10 rad per second, all of the particles have 10 rad per second. After 2 seconds, if it is 20 rad per second, all of the particles are going to have 20 rad per second. But in this case, these points are found at different location. That means the radius here and the radius here are completely differs. The tangential velocity, you have learned that tangential velocity can be given as r times omega, so that all the particles have the same angular velocity, but all of the particles or different particles have different tangential velocity depending on their radius r. So particle A, particle B as well as particle C have different tangential velocity. Why? Because they are found at different location from the axis of rotation. Therefore, here we have a tangential velocity, here we have tangential velocity, tangential velocity. All of their tangential velocity differs due to their radius r, but all of those particles could have the same angular velocity. Now we are trying to deal about a rotating object which consists the same change or the same rate of change of velocity. Suppose that this object tends to rotate and rotate and rotate and might increase its velocity. So the rate of change of increasing the angular velocity should remain constant, or in other terms, the acceleration, the angular acceleration remains constant. For such cases, we have to use a rotational kinematics equation. In rotating objects like disks or something, in translational motion, you have constant equations appears for uniformly accelerated motion. So we should have to use those equations. We'll try to see that. But first, let's try to solve one activity or one example. Suppose here you have a toy car, and that toy car tends to rotate 4 times on a table, okay, on a table in 10 seconds, and it's tending clockwise as you are observing from top of the table. Suppose here you have the table and it tends to rotate clockwise, meaning from the top of the table you'll see that the toy car is tending to rotate clockwise. How much times? 4 times. In how many seconds? In 10 seconds. Okay, in 10 seconds it performs 4 complete revolution. So it says that find the direction and magnitude of the angular displacement in rad and the magnitude and direction of angular velocity. First, you should have to determine the angular displacement, theta. Well, this toy car tends and forms 4 revolution. Theta can be expressed, previously you have said that theta can be expressed in revolution, in rad, or in degree. And it says that there it forms 4 revolution. It forms 4 revolution. So your answer should be kept in standard, and the standard unit of angular displacement is radian. And we know that one revolution is equals to 360 degree. And 360 degree is equals to 2 pi rad. So we need that the two relation, the revolution and the rad. Therefore, one revolution is equals to 2 pi rad. If so, 4 revolution is how much in rad? It's so simple, so that it's possible to use. 1 revolution is 2 pi rad. So 4 revolution is how much rad? When you crisscross, you just find that it is 8 pi rad. So the angular displacement is 8 pi in rad. In revolution, it's 4 revolution. Now let's try to determine the angular velocity. The angular velocity, find the magnitude and the direction of the angular velocity, it says. So to find the angular velocity is defined as the rate of change of angular displacement. We have defined it as the rate of change of angular displacement. So here we have found that the displacement is 8 pi rad within 10 seconds. Therefore, 8 pi rad divided by 10 seconds gives us 0.8 pi rad per second. So this is the angular velocity. This is the magnitude of angular velocity. Now the question is, what is the direction of the angular velocity? We have said that when you view from top, the toy car tends to rotate clockwise. tends to rotate clockwise. So previously we have said that angular velocity and angular acceleration have a direction along the axis of rotation. So on this turning table, it tends to rotate clockwise like this, and you have an axis of rotation through the table like this here. So as it turns, you have to use your right hand rule or screw rule so that it tends to rotate like this. You have to grasp with your 4 fingers like this. Since it's tending to rotate clockwise from top, you have to use this one, and your thumb points to the direction of downward. So downward is the direction of the angular velocity. The angular velocity is acting downward. So it says that the magnitude is 0.8 pi rad per second, whereas the direction is acting downward from the table. This is how we determine the direction and magnitudes of velocity. In this case, since the velocity remains constant, we don't have acceleration, angular acceleration. The angular acceleration is 0. And now let's see another example. A flywheel undergoes rotational motion. It tends to rotate rotational motion, and its angular position as a function of time t can be expressed as 3t squared plus 4t rad. Find the instantaneous angular velocity at the 4th second. We could have such kind of exercise or example. So to solve such kind of examples, we should have to know all the equations that you have learned in kinematics. In linear kinematics, you have learned that for a uniformly accelerating motion, we have big 4 equations. So what are those equations? The big 4 equations that you have learned in linear kinematics are: the average final velocity is equals to the final velocity plus the initial velocity over 2. And the final velocity is equals to the initial velocity plus acceleration times t. The final velocity squared is equals to the initial velocity squared plus twice of acceleration times displacement. I hope you remember all those equations, the big 4 equations in a linear kinematics. And you have to have the same expressions for rotational kinematics. For a given rotating object, we have the analogy of all of these variables. The analogy of the linear variable or the linear velocity, here the average velocity, we do have average angular velocity. For final angular velocity, we have a final, for a final linear velocity, we have a final angular velocity. Everything is going to be converted for rotational motion. So final angular velocity plus initial angular velocity over 2, this is how we determine the average velocity. The final angular velocity is equals to the initial angular velocity plus alpha t. Here also the final velocity squared is equals to the initial angular velocity squared plus twice of alpha times theta. In this case, here we do have s. S is the linear displacement. The analogy of a linear displacement in rotational motion is angular displacement. Here you have a linear acceleration. The analogy term of rotational motion of linear displacement is angular acceleration. So we can convert everything to rotational terms. Here it says displacement can be given as the initial velocity, linear velocity, t plus half times linear acceleration t squared. This was equations. And when you convert to rotational motion, the angular displacement is given to be the initial velocity, angular velocity t times time t plus 1 over 2 alpha, okay, which is the angular acceleration t squared. So you should have to use those equations. We should have to apply those equations for the questions given. So we can have different examples. First, let's try to see this example, and we'll try to solve that later. When a car is heading, let's assume that here you have a car. When a car is heading north, okay, and a man see that the wheel of a car at a distance d, the driver stamped on a brake, tries to stop the car, and the car was initially moving with 72 kilometers per hour, and then it reached to 36 kilometers per hour within 2 seconds. Okay, the radius of the wheel is 40 centimeters. The radius is already given to be 40 centimeters. Now the question is, what is the magnitude and direction of the angular velocities? And the other thing is magnitude in direction of angular acceleration, angular displacements of the wheel in this time interval. So solve such kind of problems, we should have to apply the previous equations that we have seen. First, let's try to see about the car. The car is heading to the north. In this case, the car have a translational motion. The only component which has a rotational motion is the tire. Okay, so the tire here has a rotational motion, and the tire has a radius r of 40 centimeter, or it is 0.4 meter. So we are going to see about the tire. That's it. Since the tire has a rotational or tending to move one direction. Now the initial velocity, meaning 72 km per hour, is the tangential velocity or the linear velocity of the car, initial velocity of the car. And 30 km per hour is the initial velocity of, the final velocity of the car. The final velocity means the velocity after 2 seconds. We should have to convert all this to the standard unit, which is, we should have to convert it into meter per second. So the initial velocity is 72 km per hour, and 72 km per hour can be converted into meter per second by dividing it 3.6. So when you divide this, you can find it to be 20 meter per second. The initial linear velocity is 20 meter per second. And the final velocity after 2 seconds is 36 km per hour. When you convert it into meter per second divided by 3.6 gives you 10 meter per second. Okay. Then you have the radius of the tire. The radius of the tire is 0.4 meter. The time it took is 2 seconds. Now the first question is, what are the initial and the final angular velocities of the tire? Okay, the tire tends to rotate. Well, to find that, it's very easy. We have to connect the linear velocity with that of the angular velocity. Angular velocity is related with that of the linear velocity over radius r. We have said that omega can be related v over r. Final linear velocity is 20 meter per second. Okay, the final is given to be 20 meter per second over 0.5. When you divide this, you can find it to be 50 rad per second. This is the final, and the initial, the final is 36, 10 divided by 0.4 gives us 25, and the initial is given to be 20 divided by 0.4, 50 rad per second. So 25 rad per second and 50 rad per second, this is the final, whereas this is the initial angular velocity of tire. And how do we determine the direction? We have said that the direction of angular velocity and angular acceleration are always along the axis of rotation. So let's back again here. The axis of rotation of the tire, here we have the tire, is through this. This is axis. This is the axis. If you have the other tire, here we have the axis. So the axis shows you either to the direction of east or to the direction of the west. And the car is tending to move upward, so the tires are tending to rotate on this direction. So when you apply your right hand rule, it points you to the direction of west, meaning the direction of the angular velocity is along the west. So you can put your answer like this. The final angular velocity is 25 rad per second. It's acting due the west. The initial angular velocity is 50 rad per second. It's acting due west. And then how do we determine the acceleration, the angular acceleration? Well, to find the angular acceleration among the given, previously we have different equations. Among these equations, you should have to choose the appropriate equation. Here we have omega is equals to omega initial plus alpha t. So how do we determine the acceleration alpha? To find the acceleration alpha, we know that alpha can be given as the final angular velocity minus the initial angular velocity over the time interval t. The final angular velocity is 25, the initial is 50 over 5. So when you are trying to calculate this, you could have minus 25 over 5 minus 5 rad per second squared. Negative 5 rad per second squared is the acceleration, the angular acceleration. Here it says minus. Minus means you should have to invert the direction. So far we have tried to see about the direction of the angular velocities are acting along the west direction. Here it says negative. Negative means you should have to convert the direction of, you should have to reverse the direction of the angular velocity. Previously we have said that angular velocity and angular acceleration are always acting along the axis of rotation. If it is a very fast moving, the angular acceleration has the same direction as that of the angular velocity. But if it is moving slower and slower, the angular acceleration tends to oppose the angular velocity. In this case, the negative value indicates that this object is slower and slower. Initially, it was 50 rad per second, and gradually it's decreasing and decreasing and reached to that of 25 rad per second, so that it is a slower moving object. The angular acceleration opposes the direction of angular velocity. It says 5 rad per second. It should be to the direction of east. The result is 5 rad per second squared due east. The negative sign converts the direction. The negative of west is east. So the negative of rad per second due west, it says. But the west is the direction of the angular velocity, and here you have the negative value, and that negative value switches the direction, and it is 5 rad per second due east. Okay, this is how we determine the direction of angular velocity and angular acceleration. Now at last, the third problem asks you to find the angular displacement of the wheel in this time interval. How do we determine the angular velocity? I mean the angular displacement. Among the given, previously you have different equations. Among these given equations, which one is appropriate to find angular displacement? This one or this one? You might choose any of the two as you like. So let's take this equation. You might use this one actually for you. Try to practice on that. Let's take this one. So theta is equals to omega initial t plus 1 over 2 alpha angular acceleration t squared. This is how we determine, or it's possible to use this one, anything as you like. Therefore, in our case, we do have the initial angular velocity to be 50 rad per second. The time it took is 5 seconds. So plus 1 over 2 minus 5 squared gives you 187.5 meter. I mean, it gives you rad, so we can convert it into meter. So this is how we determine the angular velocities and angular acceleration. So far we have tried to find and express the rotational equations on different equations. You have learned about instantaneous and tangential, instantaneous and average velocity, instantaneous and average acceleration in your linear concept. Okay, so the third question said that try to find the angular displacement of the wheel in this time interval. So to find the angular displacement theta, we should have to use among the equations provided here. You can use either of these two. It's possible to use this one or this one. Suppose that, let me take this equation. So it said that theta is equals to omega initial t plus 1 over 2 alpha t squared. This is how we use. Therefore, to use theta is equals to omega initial, we have previously given to be 50 rad per second, and omega final is 25. Actually, we should have to use the initial angular velocity. The initial angular velocity is 50, and the time it took is 2. Okay, here it says 2 seconds, so we should have to put 2 plus 1 over 2. We have already found the acceleration here to be negative 5. Okay, you should have to put the negative sign as well, negative 5 rad per second, and the time it takes is 2 seconds squared. So when you put these two, it gives us 100, and minus this gives us 2 squared is 4. When you divide by 2, it gives us minus 10. Okay, so 10 minus 100 minus 10 gives us 90 rad. The unit is rad. We have said that meter over meter can be given as rad. Okay, so let's take that the angular displacement found here to be 90 rad. Okay, so far we have seen how to determine the angular velocities, the direction as well as the magnitude, and then we have found the direction and magnitude of angular acceleration, and at last we have also tried to see how to determine the angular displacement. This is how we apply rotational equations. And in your kinematics concept, you have also learned about how to determine instantaneous velocity and instantaneous acceleration, as well as average velocity and average acceleration. To recall that, you have learned to find the average velocity as the change of displacement. Okay, that means the position of a given particle at time t2 minus the position of a given particle at time t1 over time t2 minus time t1. This is how we determine the average velocity. The same thing appears for rotating objects. You can have the average angular velocity can be determined as the rate of change of angular displacement. Meaning, if you have angular displacement expressed in terms of time t, it's possible to have displacement at time t2 minus displacement at time t1, the angular displacement at time t1 over t2 minus t1. It's possible to have such an expression. As well, for instantaneous velocity and instantaneous acceleration, you have an expression. It says that velocity instantaneous can be given as the derivative. I hope you have learned it in your mathematics lesson, the derivative, the first derivative of displacement. So when you differentiate displacement as a function of time t, you can find velocity instantaneous. The same thing is true for angular parameters. Angular velocity instantaneous can be determined as the derivative of angular displacement, like this. It's also possible to find instantaneous angular acceleration, alpha instantaneous, using the first derivative of omega, which is, if you have omega means angular velocity function as a function of time t, it's possible to differentiate it or derivate it and find the instantaneous acceleration. Suppose let's have one good example, the example that we have previously seen. A flywheel undergoes a rotational motion. It tends to rotate. And its angular position can be expressed in terms of time t. So the angular variables can be given as 3t squared plus 4t. This is in rad. Okay? This is the angular displacement which varies with time t. As the time changes, the angular position of the rotating flywheel changes. Now the question is, find the instantaneous angular velocity. Here it asks us to determine the angular velocity. Well, angular velocity can be given using limit or derivative concept. You have learned about derivative concept. So you should have to derivate the displacement function with respect to time t. Therefore, the derivative of this gives you should have to put 2 to the first coefficient. So 2 here, 2 times 3 gives you 6t, plus t would have the power 1. When you put it aside here, 4. Okay, so 6t plus 4, here it says in rad, over time gives you rad per second. Okay, per second. This is the angular velocity time expression, meaning the angular velocity varies with time. But here we are asked to find the angular velocity at exactly 5 seconds. This is how we determine instantaneous velocity and instantaneous acceleration. To find this, the instantaneous velocity at time t equals to 5 seconds. So here we have 5 seconds. We should have to put 5 in terms of time t. Sometimes there might be equations with no time t. In that case, whether the time changes or not, the velocity remains constant. But here you have a time variable, so that as the time changes, the angular velocity also changes. In this case we are asked to find the instantaneous angular velocity at 5 seconds. So you should have to put 5, 6 times 5, 30 plus 4 gives you 34 rad per second is instantaneous velocity of this flywheel, whose angular displacement is expressed in terms of time t. So it's possible to have angular velocity and angular acceleration as well. So this is all that I have got for today. So far we have tried to deal about the rotational kinematics, the different types of motions. Among the different types of motion, we are trying to deal about a motion having a constant angular acceleration. Therefore, we have seen the big 4 equations: the average angular velocity, how to determine the final velocity is equals to the initial angular velocity plus alpha, the angular acceleration times t. We have also seen that the omega final squared is equals to omega initial squared plus twice of alpha, the angular acceleration times angular displacement theta. And at last, we have also tried to see how to apply angular displacement theta is equals to omega initial which is the angular velocity initial times t, plus 1 over 2 alpha t squared. So this is all that I have got. Next time we'll try to see the other concepts. Bye bye.